All right, getting into 1.6, something we've already actually talked about a little bit, which was just from rules of transformations of graphs. Most of these rules you're going to be familiar with. I know you guys did some horizontal translations and vertical translations and reflections and all that kind of stuff. There may be a little bit new here for you, so we're going to start with this next page. I created just a list of all the rules for you, so you could kind of have them all together in one page this way. So these, let's see, here for sure, I know you guys would have at least done those last year. I don't know if your teacher got into stretches and compressions, so this might be the new portion of it, but I know you would have at least done all of those. And so here's just a quick reminder of those rules. The things that are not attached to x, and this is consistent all the way through, the things that are not attached to x are going to affect your graph up and down. Right? So if you see a plus something or a minus something at the end or at the beginning that is not directly attached to x, you're going to have a vertical translation. And so here's what would happen. It's just a shift up or down in terms of those guys. However, if it is attached to x, because you can see this is now grouped in the parentheses with x. So now it's attached to x. So whenever you see something attached to x, it will affect your graph left and right. And here's kind of a general rule of thumb that you can apply. The things that are not attached to x that affect your graph up and down directly do what it looks like they would do. So if it's a plus, it goes up. If it's a minus, it goes down. However, the things that are attached to x and they affect your graph left and right pretty much do the opposite of what you would expect them to do. If it's a plus, it goes to the left, as you can see right here. And if it's a minus, it would go to the right, like you see right here. So as a general rule of thumb, that's the way that you can see your up, down, left, and right activity going on there. So the reflections, again, if it's not attached to x, it's going to reflect your graph up and down across the x-axis. If it is attached to x, it's going to affect your graph left and right over the y-axis. Right? So here's just kind of a rule that you could apply to those. So here's the ones that I think might be a little new to you. So if you have a number that is being multiplied to your function, not attached to x, again, if it's not attached to x, it's going to affect your graph up and down. And the things that affect your graph up and down do directly what you see here, just like I mentioned up above. So if it is not attached to x, it's going to affect your graph up and down, and it does exactly what you would see here. So if this is 2 times the function, then I am doubling the y value. No, that's pretty much the same. What these are saying is if it's a number that's bigger than 1, basically it's going to stretch your graph up and down. If it is a number smaller than 1, so if it's between 0 and 1 like you see on this one, it's going to be a compression. It's going to shrink your graph vertically. Right? And so that's what you're seeing here. But really on those, it's like whatever that number is, if you multiply it times your y value, that's going to be the new point. Okay, whether it makes your graph taller or shorter, depends on what that number is. Okay, so here's the horizontal stuff. So again, you can see this is now attached to x. And anything that is attached to x affects your graph left and right, and it does the opposite of what you would expect it to do. So the vertical stuff does exactly what you would expect. However, the horizontal stuff does the opposite of what you would expect. So if I multiply my x times a number, like let's just say this is a 2. So if this is 2x, then it's going to affect my x coordinate, but instead of it being 2x, it's going to be x divided by 2. So again, the horizontal stuff does the opposite of what you would expect. Right? So these are x over b in these cases. So those are kind of all the rules in a nutshell put into one page. We're going to do a few practice rounds on this. I just wanted to mention something first. So right below that table, I put sort of your order of operations that you would do, because you might have things that do a bunch of those rules within one graph, and we have to know which ones do I do first, or does it matter? And if it does matter, so here's kind of a list of the order of operations, and I just made a note that basically says it's basically just your basic PEMDAS is what you're seeing on that. So we got to deal with our parentheses first, right? Which would typically mean a horizontal shift, something we have to take a look at. Next would be multiply and divide, which we just talked about up above, which is your stretch or compressions. Then you would do your negation or reflections, and then last, always last, would be a vertical shift, which is the addition and subtraction, which are the top two rules on that table up above. The issue with stretching and compressions are a little tricky because oftentimes you could view something either way. Like you might say a vertical stretch could actually be seen as a horizontal compression. So just to give you maybe a visual here. So let's just say this was the original graph, right? So if I say I have a vertical stretch on that, which would now look like this. So here's my vertical stretch. Well, someone might look at that and say, no, you didn't do a vertical stretch. All you did was take this and do a horizontal compression on it, right? And those can both be right. So sometimes a vertical stretch you could also identify as a horizontal compression. Sometimes a vertical compression could also be seen as a horizontal stretch. I know it sounds a little confusing, but we're going to get some practice on this. So here's one idea I just threw in here to give you an example. Here's the original. This is my absolute value function, parent function. So there's a point on that at 2, 2. Right? So if I wanted to do a vertical stretch on that by putting the 2 out front, so remember this is not attached to x, which means it's a vertical stretch. So it means I would multiply the y coordinate by 2. And these are the rules that I gave you up above. So anytime you have something not attached to x, it's going to affect your graph vertically. And since this is being multiplied, right, we're going to see this as a vertical stretch, and it's going to affect my y coordinate, just based on the rules you saw up above. Right? And so here's a new point that I would now have. Well, what if we also said, no, instead of doing a vertical stretch, I want to do a horizontal compression. And if you look at what we did up above, horizontal compressions, remember we said if it is attached to x like it is now, so this one is not attached to x, this one is directly attached to x, so now it's going to affect the x coordinate, and as we already talked about up above, it does the opposite of what you would expect. So here was the original. I need to divide my x by 2, and so here's the new point that I would get from the original. Right? I just divided my x by 2. Well, if you look at that, these points are on the same graph if you were to graph them both. Right? So this one doubled the y, this one just cut the x in half, but they're still on the same graph. So let me show you. So let me start with both of these at the same time. Actually, I'm going to clear this out just so it regraphs it for you. And I'm just going to throw one in just to clear out the memory of my graph here real quick. So I'm just throwing that in. So let me get back to this. So if I were to graph both of these, one with a vertical stretch, one with a horizontal compression, you're going to see it's actually the same graph. So I'm going to do 2 times the absolute value of x. I'm then going to do the absolute value of 2x and put them on the same grid, and you're going to see these are actually the same graph. Let me see if I can try to eliminate that glare for you guys. Hold on. There we go. So watch what happens when I hit graph. It's going to graph this one first, and then this one's going to come up second. So this one is in blue, and then the second one's going to be in red. So I'm going to hit graph. So first we're going to get the blue one, and then here comes the red one. Directly on top of it, you can see they're actually the same graph, right? So all that is to say, these can be viewed sort of in different ways, but they can still be both the correct answer. Okay, so hopefully that added some clarity to those. Let's do some practice. Just a reminder of your basic rules that you've learned in the past. Here's the parent function. Okay, so here's the parent function. What this is telling us to do is to take that function and add 2 to it. right? So according to the table that I showed you at the start of this video, this is not attached to x, which means it's going to affect my graph up and down. It's +2, so I'm simple. And you know what? So what they want us to do is they actually want us to take this graph and shift it up 2. They gave us kind of a weird vertex, though. It's kind of like at 0.5, and then this is like deeper than -2. Let me just add some clarity to this. I'm going to give us the basic parent function of a parabola, and we're going to go off of this. This will be easier to throw in our transformation rules. So we're going to take that blue graph and we're going to shift it up 2. So we're going to call the blue graph f of x. And we're going to shift it up 2. So we know it would now look like this. At any time, feel free to pause and do any of these ahead of me to see if you're doing this right. Here is a reflection of this graph. We're always coming back to this as f of x. So we're going to do a reflection of f of x. Again, this is not attached to x, so it must flip my graph up and down, which means my new one would look something like this. Okay, so here's one. So now we're going to multiply 2 times the entire function. It is not attached to x, therefore it must affect my graph up or down. And remember what this would do is it would multiply the y values by 2. Okay, it would multiply the y values by 2, which means I'm going to get a vertical stretch on this, and it's going to do one of these guys. So let's just take a point so I can, we're still going to be at 0, 0. Let's just take a common point here. So if I had the graph, or the point 1, 1, right, on my graph, which is where my parent function would go through, right, it would double the size of the y value. So 1, 1 would become 1, 2. And so instead of being here, it would now be here. And so the original one was wider. The new one would become skinnier. So this is a vertical stretch of the original graph. So you see how some people could say that this is a vertical stretch. Someone else might look at it and say, no, no, this is a horizontal compression, right? And it would still really be an accurate description no matter which one you said. Okay, so let's jump down to this one. We're getting a new graph. And let's see if we can use their graph this time. So here is the new f of x. And one point that we can make note of is 0, 0 can be a common point here. So that can be one that we can use. 1, 0 is a point we can use. -2, 0 can be a point we can use. So let's see if we can use those and apply this information. So first things first, this is in parentheses, which means it is now attached to x. Remember, it's going to affect our graph left and right, and it will do the opposite of what we would see here. So this is going to go right 1. So we're actually going to take all those points, and they're going to go right 1. So we're now here, here, and here. And let's draw that same curve as best as I can anyway, through those points. Sorry, I should have gone up higher. Something like that. So we went right 1 on those. Here we now have a reflection. So this is now, this negative is attached to x, which means it needs to do a reflection left and right across the y-axis. So because it's attached to x, it goes left and right, which means a point that was over here is now going to be over here. And a point that was on the right side of the y-axis is now going to go to the left side of the x-axis. So that guy would have to go here. So this, right, this curve, this whole piece is being reflected across this guy. It's now going to go like this. And well, whatever was on the left side, that curve, is now going to be on the right side. So it should do something like this. See if I can draw that here within our new points. So something like that. So that's supposed to be our, so here was the original, this dark one, So if I reflect this across the y-axis, this would be our new graph. And last one over here, let me give you a horizontal compression. So we are going to multiply the x-coordinates, or sorry, I should say divide the x-coordinates by 3, right? So it's gonna horizontally shrink our graph if I divide my x's by 3. So something that was at, I'm going to write these out, maybe this will help. So something that was at negative 2, 0, if I divide that by 3, is now going to be at negative 2/3, 0. Right, would be the new point. So now it's like negative 2/3, 0. 0, 0 would still be 0, 0 if I divide those by 3. So that point is going to stay. Let's take this point over here. So this was originally at 1, 0. So 1, 0 is going to become 1/3, 0. So my x's are all being divided by 3. So again, it's like taking this graph and it's going and just shrinking it and doing a horizontal compression on it. So it's now going to do something like this. Sorry, that went up to 2. So this and this should still be just as high and just as low, but it should be squeezing in the x-coordinates, right? So we get a squeezed in version of this, right? And so there's our basic rules. So there's just some examples for you. Let me go back to the first page. So we can get into some of these here. So on this first one, what they wanted you to do is they're saying, okay, here's the original. What would the new equation be if I wanted a reflection of this over each axis? So we're going to do each one of those separately. So remember, if I wanted to do it across the x-axis, in other words, up and down, the negative would apply to the entire function, right? It's like it's out front. It would apply to every term in the entire function. So they're taking this, and they're just putting the negative out front. That's our negative right there. So what that's essentially going to do, and you could leave it like this, that would be fine. If you wanted to, you could also distribute this to both of those and write it this way, and that would mean the same thing. So whether you put it out front or you distribute it across the numerator, it would mean the same thing. So either one of these would be an acceptable answer for the new reflection across the x-axis. When you reflect across the y-axis, right, it's this look. So this is now going across the y, which is left and right. So the negative is now attached to x, which means essentially all I'm doing is I'm changing all of my x's to negative x. Okay, so this x is becoming negative x, and so is this one. And so here's what that would look like. And then if we did a little cleanup on that, negative x squared is still x squared. Right, but this one would now become negative 3x. So it really helps just to apply the rules on those guys in order to get that. So here's the best answer for the second one. Let's try one. And we can check these on the graphing calculator after we've done it just to make sure it looks correct. So let's just follow the rules on these ones. So if I wanted to reflect this guy across the y-axis, in other words, I'm going to reflect it left and right. That means f of x would become f of negative x. So all I have to do is replace my x with negative x in order to get the reflection across the y-axis, which is left and right. Okay, so on this one, it is now going to be simply negative x minus 2 plus 1. So if you graph this in your graphing calculator and graph this one in your graphing calculator, you should see a reflection of this across the y-axis when you graph this. Okay, and so if you wanted to do the other one up and down over the x-axis, so anytime I want to do something that's up and down, I need to apply the negative to the entire function. So I'm going to apply this rule right here. And so basically we're going to say I need to apply this negative to the entire function and do this. So we're going to do the opposite of the entire function. So probably the better way of writing that would be to distribute that negative, and I would write it this way. All right, so again, if you were to graph this one on your graphing calculator and this one on your graphing calculator, this should be a reflection of this guy across the x-axis, or up and down. All right, let me move on. Oh, I guess we could do this one as well. I'll do this real quick. If you don't need another example, you can skip ahead on this part. If you do need another example, you can follow along on this one. There was a side note on this one that I wrote in here that I wanted you to see. If I do this one, remember what we learned earlier was that anytime you do a reflection across the y-axis, that represented an even function. So this one is already an even function. So what's going to happen if I replace x with negative x? Well, negative x squared is still x squared in both locations. So on this one, if it's an even function like this one is already being reflected across the y-axis if you graphed it, which means if I do a reflection across the y-axis, I'm just going to get back what I started with. Okay, so in this case, if you do f of negative x, you're simply going to get back what you started with. So this is already a reflection across the y-axis. However, if you wanted to do reflection over the x-axis and do negative f of x and distribute this to the entire thing, so negative 3x squared over 4x squared minus 1, you could write it this way, and that would work. If you wanted to apply the negative to the numerator, it means the same thing. So if I wrote it this way, this would also be an accepted answer. Always good to know both. Oftentimes, if you're checking like an answer in the back of the book, you might have written your answer one way, they might write their answer another way. Good to know that they mean the same thing so that you know you're still correct, no matter which way you put it. All right, let me move ahead here. So on these guys, they're giving us this original function, and they're saying, if I were to apply rules like this, what would the new function be? So we're starting out with x to the third minus x. So if we wanted to apply a vertical stretch, so remember, anything up or down is not attached to x. So if I wanted to apply a vertical stretch by a factor of 2, right, that just means I'm going to multiply the entire function by 2. Okay, and so if I were to distribute 2 to that whole function, and that's what they're trying to show you right here, this is what the new one would be. The tricky ones are anything that does left and right, because these are always the opposite of what you would think. So if it's a horizontal shrink of a fourth, remember that means I am dividing my x's by 1/4. Well, dividing your x by a fourth is the same thing as multiplying by 4, right? So they actually did a good job here of showing you both looks on that one. So here's the rule, right? If I'm going to divide my x's by a fourth, that is the same thing as calling it 4x, right? And so this, I'm going to see this as my horizontal shrink of a fourth. I'm going to replace my x's with 4x. So now it's 4x to the third minus 4x. And we could do a little cleanup on that, and this is the look that we would get. So let's try some of those on our own here. Always a good place to pause and try this ahead of me, if you would like. But let's get a little practice. So this one says negative x to the third plus 5x. So we're going to do a horizontal stretch by a factor of 2. So remember the horizontal stuff. So if I have a factor of 2, remember what we saw in the very start of this video, that if my horizontal stretch is a factor of 2, that means xy is becoming x over 2 comma y, right? So in other words, my x is being replaced by x over 2. So that means I'm going to replace my x with x over 2. So it would look like this, and let's just do a little cleanup on that. So I would rewrite this as negative x to the third over 8 plus 5x over 2. So this function now represents that horizontal stretch of this one by a factor of 2. So vertical shrink by a factor of 0.5. Remember, the vertical stuff tends to be a little simpler because it does exactly what it says it would do. So the vertical stuff affects your y values. So I'm simply going to multiply my y's by 0.5. In other words, I'm going to multiply this whole thing by 0.5. So if I multiply the whole thing by 0.5, so 0.5 times 2x cubed plus 4x squared. So that's what they're telling us to do with that vertical shrink of 0.5. A little cleanup on that as we distribute. Should be looking at x to the third plus 2x squared. And that would be our answer. All right, so take a look at this. Almost done. Trying to move through it quick here for you. So now they're going to start throwing a few rules all at once together at us on these guys. So for this example, they're giving us a specific order that they want us to do things in. So they're saying, we first want you to do this, then do this, then do this, right? And so they're giving us a specific order. This isn't the whole PEMDAS, we do things in the order of operations, because they're not saying to do all these things in any order. They're saying, here's a specific order that we want you to do them in. So the first thing they do is they do all 3 of these in this order. So they're doing them in that order. And then in part B, they're going to do it in the opposite order. So they're actually going to do the vertical shift first, or sorry, the vertical translation first, then this, and then this, right? And so what we're going to do is we're going to show that comparison to show that the order in which we do these things does definitely matter. So when it comes to them just giving us a function, we need to make sure we're doing things in a proper order, okay? And so if they started out in part A like this, so here is the 3 units to the left. Then they're going to put in the vertical stretch factor of 2. And then it's going to go down 4. All right, and so here's what that would look like. And if you did expand it, you could write it this way as well. So we could really write this in either order. Or sorry, either method here. They both mean the same thing. So take a look at B though. B, you're going to see we don't come out with the same answer. Right? So if I do things in the other order, so we're going to start with this, then this, then this. So let me flip this over. So here's what happened if you did it the other way. So we first did this, shifting down, then the vertical stretch of 2, and then we got the horizontal translation. Right? So if we did it in that order, clearly not the same answer as what we got on the previous page. So let me give you a couple of those if you want to do these for practice. You can always do one of these for practice and then skip ahead to the next example. If you want to do both of these for practice, then you can do that as well. So you can kind of go at your own pace here for however your learning is going. So here's the original, x squared, and we're going to do a couple things here in order. So if we were to do x squared and do a horizontal shift 2 to the right, what would that look like? All right, so 2 to the right would be this. And now we're going to do a vertical shrink by 1/2. And remember, the vertical stuff, we just take it at face value. I am multiplying the whole thing by 1/2. So that would be this. And now we can do the translation 2 units up. by simply adding 2 at the end. And that's what our finished product would look like. On this one, so they're saying, let's do the same thing. We're starting with x squared, and we're not going to do a horizontal shift. We're going to do a horizontal stretch by a factor of 2. So remember what that looks like. So in a stretch, and I'll just put this off to the side, remember f of x would now become f of x over 2. So the horizontal stuff always does the opposite of what you would think. So instead of multiplying by 2, it's dividing by 2. Right? So this is what's happening. So x is becoming x over 2. And you could expand that if you wanted to write that as x squared over 4. That would be fine. But at the end of that, we're going to go 3 units up and add 3 onto the end. So we could write it this way. If you wanted to write it as x squared over 4 plus 3, that would be fine as well. Either way is fine. For this last example, and then we'll be done with this section, we're now just applying it to a graph. So they're saying, here's the original graph, and we've already started the video with some of these. They want you to apply a few of these. Here's where now you got to take into consideration the order that you're doing this in. And I want to link this one back to an acronym that I'm sure you learned in Algebra 2 last year. You probably got the acronym HI 15. So your horizontal translation, reflect over the y-axis, reflect over the x-axis, and then your vertical shift. Right? So you probably got the acronym for HI 15. That's your Roman numeral 15 right there. So totally works on these. I'm going to add one extra piece to it though. Instead of HI 15, we're going to call it the Pch 15. So that S right there now can take care of your stretch or shrink, right? And so that's what this represents. So that's a great place to start. These guys can be interchangeable, which is why you can either do the whole PEMDAS idea with parentheses and then multiplication. So like parentheses and then multiplication. I just like it this way because now you have like an acronym that I know you're already familiar with that you can apply as well. So we're going to call it Pch 15. You can do your stretches and shrinks first. So if they're giving us this, we need to know the order in which to do that in, right? And so we can do here's the original graph. So I'm going to do my stretch first. So this is my vertical stretch. We are multiplying the y values by 2. And you get this. So that was our stretch. Then if there's a horizontal shift, I could now apply it. So I'm going to go, according to this, I'm going to go right 1. And you get this. There's no negatives up there, so there is no reflection over the y-axis. There is no reflection over the x-axis. So let's go down to the last one and do our vertical shift, which is right here. And we can go up 2. And sorry, that actually should be down 2. It looks like they have a little typo right here. This is what they wanted, and it's what they actually did. And right here, they accidentally put a plus instead of a minus. So little typo right there, that should be minus 2. So that's why the final step right here should go down 2. And so that's the graph that we would finish with. So great acronym. I would encourage you to just apply this. Stretches and shrinks first. So that's your multiplication. Then you can do your horizontal shift. Even though these guys can be interchangeable, this is just a great little acronym to help you, right? Then your reflections over the y, over the x, and then your vertical. All right, so let me finish off the video. If you're good to go on that, you can end it. If you want practice, let me give you a practice. All right, so we'll knock these two guys out here real quick and we'll be done with this section. So you got two things going on for this graph. They want you to do the vertical stretch of 2 and then the vertical shift down 1. So we know in the Pch 15 that the vertical stretch would come first. So I'm going to multiply my y coordinates by 2. So -1, 0 would still be -1, 0. 0, 2 would become 0, 4. 1, 2 would become 1, 4. And 2, 0 would still be at 2, 0. So here's my vertical stretch. Would now look like this. So it's stretched vertically. Now I could shift the whole thing down 1 to finish it off. So you go down 1, you go down 1, you go down 1, and you go down 1. And so here would be the finished product that I'm drawing right now. And that's where it would end. Always kind of cool if you can do these in like different colors or something like that, or even on multiple grids, so you can actually see the finished product. But keeping life simple for now. So last one here, you got 3 things taking place. You have your vertical stretch, you have a horizontal shift, you also have a vertical shift. So again, in our Pch 15 process, we're going to do the vertical shift first. So multiply your y coordinates by 2. So again, you're going to stay. Let's see, you're going to go up, you're going to double, you stay. So you are here. Now I would go to the right one. That's the next order of operations in the Pch 15. So if we did everything to the right one, you go here, he goes to here, that one went over to here, and that one went over to here. So what you would find on this is, what if I had done this before this? Would I get anything different? And you would not. That would have come out to be the same place that I'm at right now in the graphing process. So those guys, again, are really interchangeable, but if you like the acronym, you can stick with your stretches and shrinking first. Now I can do the whole thing down 1, so I'm simply going to take those 4 points, move all 4 of those down 1, and that would be your finished product. And so that's it for 1.6.